All right, so welcome to section 7.3. In this section, we're going to take a look at an introduction to probability. So we're going to begin by taking a look at the terminology necessary, and then we're going to take a look at connecting those things we did in the last section with the sets and the set operations to the idea of probability and how those things kind of link and map over. All right, so our objectives for this section are to take a look at what is a sample space and how to identify simple events. We'll take a look at that fundamental counting principle, classical versus empirical probability, and find probability using complements. All right, so this is the first section on probability. So of course, a big thing in this section is going to be the idea of some terminology specific to probability. So we'll take a look at those pieces of terminology to begin with. All right, so our probability experiment. Our probability experiment, by definition, is an action or trial through which specific results, counts, measures, responses, however you want to word that, are obtained. Now, that's kind of a useless definition because it's so generic that it doesn't say anything. So when we think about a probability experiment, that's the thing that we're going to do, that we're going to try to find the likelihood of occurring. So think of it like this. This is the flip a coin. So the experiment is to flip a coin or to roll a die or to pick a card. Now those are all very classic probability things to do, flipping coins and rolling dice and picking cards. But even something as complicated as predicting the weather can be thought of as our probability experiment. All right, more terminology. Outcome. An outcome is the result of a single trial of your experiment. So if you flip a coin and it lands on heads, you have just received an outcome for that experiment. The outcome was coin landed on heads. So it is the result of a single trial. So one flip of the coin, or one roll of the die, or one pick of a card, or one prediction of the weather. Okay? Sample space. The sample space is the set, so think back to section 7.1 through 7.2, the set of all possible outcomes of the experiment. So everything that could happen. Now, let's take a look at this word. Everything that could happen. So we are going to be flipping coins and rolling dice and picking cards in this section. And so when we do these things, when you flip a coin, it can land heads or tails. We don't have coins that balance on their edge. When you roll a die, it lands with one of the faces up, and you can count the dots, the pips. That's what they're called, PIPS, pips on the up face. We don't have dice that land on their edges. We don't have coins that balance on an edge. We flip a coin, it's heads or tails. We roll a die, it's 1 through 6. Right? Speaking of dice, right? Die, singular. Dice, plural. If there's one of them, you're rolling a die. If it just says die, that means the standard 6-sided die. If it wants you to be anything other than 6-sided, it will tell you. There are 4-sided, 6-sided, 8-sided, 10-sided, 12-sided, 20-sided dice out there. Did I say 8-sided also? There are others, but those are common dice. If it just says die, it's a 6-sided. If it's anything else, it's going to tell you. Okay? We also assume that the things that we're doing are fair, meaning that they're not in some way rigged. So we don't have dice that land in a certain way because they're weighted or something. Okay? All right, so more terminology. We've got event. An event is a subset of a sample space. So it consists of one or more outcomes, and it is a subset of our sample space. All right, so let's take a look at some examples. So on the left here, I have the experiment, the probability experiment. On the right, we're going to have the sample space. Right? So our job is to give the sample space. So if that's my spinner and I spin it, my sample space then, and we usually use the letter S to represent the sample space. Remember, sample spaces are sets. So it's going to be the set 1, 2, 3. Because if I spin that spinner, that's how it's going to land. Now, if you're one of those people out there going, what if it lands on a line? Maybe we'll just say that if it lands on a line, it's considered no spin, and we spin again. So we only consider it a valid experiment if it lands in one of the regions marked. Right? How about if the experiment was to toss 2 coins, right? And a head or a tail is recorded for each coin. So what would be the sample space? Well, my sample space is going to be, well, both coins could land heads, so that would be head, head. Or my coins could land heads, tails, one of each. Or it could land tails, heads, one of each. Or it could land tails, tails. Now, one of the things about this is sometimes people get confused by is they look at those two and they want to say, aren't those the same? Mathematically, no, they're not. And so one way to help you understand this is when it says 2 coins, it doesn't say they're the same coins. So what if the 2 coins were a nickel and a quarter? Then this one heads and this one tails would be very different from the nickel tails and the quarter heads, right? Do the same thing if you're thinking about dice, right? Think of one die being a red die and a blue die, or a red die and a green die, and then a 2-3 would be different from a 3-2, right? So keep that in mind. We want to list all the possible outcomes. All right, so remember our definition up here said that our sample space is a set. So when we define these things, we're going to use proper set notation. We give it a name, right? We use the brackets to say it's a set. We list all the elements of the set. We separate the elements with commas. Okay? Now, if you wanted to, you could go fancy and use set builder notation. What will we have to say here? 1 is less than or equal to x is less than or equal to 3, and x is an element of the integers, or something like that. That'd be a tough one. Unnecessarily complicated, because for a set this simple, why don't you just go 1, 2, 3? All right. Now, as the experiments get more complicated, defining the sample space can get a little harder. So here, let's take a look at this last one. Suppose a coin is flipped until both a head and a tail have been seen, or until the coin has been flipped 4 times, whichever comes first. So I'm flipping a coin until I've got both a head and a tail, or until the coin has been flipped 4 times, whichever comes first. So I have to flip it at least 2 times. So I think the smallest could be those two, head first then tail, or tail first then heads. Or you could have head, head, tail. That would be 3 flips to get both a head and a tail. Or it could be tail, tail, and then a head. Or 4 times. Okay, so these two would represent all the ways the experiment could end with only 2 flips. These two represent all the ways the experiment could end that would require 3 flipping of the coin. Now we're going to have to do all of the 4 flips of the coin. Let's see. How about head, 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 tail? That would end the experiment. Tail, 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 head. That would end the experiment. But also head, 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 head would end the experiment, because whichever comes first. I'd have 4 flips and never saw both. Or I could have tail, 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 tail. And these would be the ways that the experiment would end with 4 flips, and we have seen both a head and a tail. And then these two would be the ways that the experiment would end by just having 4 flips. Okay. All right. So keeping that experiment in mind, we're going to continue with that same experiment. Well, what happened? Yeah, okay, there we go. that idea of flipping the coin 4 times. And let's take a look at then writing events. Now remember, an event is a subset of a sample space. That's our sample space right there, right? So then each of these events down here, that's a horrible arrow, but you get the idea. Each of these events down here is going to be a subset of that sample space. Okay? So the first event is the coin is flipped exactly 3 times. So I'm going to call that A, the event A. And so which elements of that sample space have the coin being flipped exactly 3 times? Well, those are the 2 that I highlighted in blue, HHT and TTH. The event, coin flipped exactly 3 times. How about the coin is flipped at least 3 times? Right? Well, what does at least 3 times mean? That means 3 times or more. So that's going to be the blue, the green, and the yellow highlights. So here's the exactly 3 flips. And here's the at least part of it. H and then T, 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 T. Trust me, that's 4 T's right there. And then part C down here is the event that the coin is flipped only 2 times. Well, that'd be the pink from the highlight. So that would be event C. And that would be heads, tails, tails, heads. All right, so we're working with experiments. We're trying to find the probability of an experiment. When we have an experiment, someone will tell us what the experiment is. We'll set up a sample space. They'll tell us what the experiment is. We'll set up a sample space. They'll tell us what the experiment is. We'll set up a sample space. Then they'll give us an event. We'll figure out what's in the event. They'll give us an event. We'll figure out what's in the event. They'll give us an event. We'll figure out what's in the event. And then we're going to calculate probabilities of these things happening. Like, what is the probability that the coin will only be flipped 2 times? What is the probability that the coin will be flipped exactly 3 times and such? Okay? So working through those scenarios. All right. Remember set operations? Set operations for events are also valid. Intersection, union, complement. We talked about all these in 7.1 and 7.2. They're still going to happen here. For example, if I have 2 events and I want to talk about the intersection of those 2 events, all I'm saying is, there's my notation, that this just means that E and F will both occur. So the intersection of 2 events is the event containing all the elements that are common to both of them. So there's nothing new about this. We're just applying it in a new way. We know what a union means. So what does it mean if we're talking about events? It just means E or F or both occur. Now this one's a little tricky because of the word or. Because remember, we have to use the math or. The inclusive or, not the exclusive or. Okay. And then the complement. I know what the complement means. It just means everything outside, but still in the universe. But here our universe is just our sample space. So then saying the complement of an event is just saying that E does not occur, right? All right, so let's take a look at our basic probability principle. For sample spaces with equally likely outcomes, the probability of an event is defined as follows, and blah, 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 blah. But I want to stop right here and take a look at this. Sample spaces with equally likely outcomes. Equally likely outcomes is a probability phrase that states or means or implies that all of the outcomes in the sample space have the same chance of occurring. So I'm going to go back up here and take a look at some things. Now, I'm going to erase a bunch of highlighting that I did here to clean this up a little bit, but I want to go back and take a look at some of these. For example, and I'm going to look at the spinner example. The spin the spinner experiment has an equally likely outcome sample space. Now, we don't need this one, so I'm going to go ahead and get rid of it. But what that means is that spinning a 1 or spinning a 2 or spinning a 3 has the same chance of occurring. When you look at that spinner, you'll see that the spinner pieces appear to have the same size. Right? Now, that would not be true if our spinner had been set up like this, where piece 2 would be way too big, so it wouldn't have the same chance of occurring. So an equally likely outcome experiment is an experiment where all of the outcomes in the sample space have the same chance of occurring. That one, equally likely. This one, equally likely. The coin can land either way. So getting 2 heads is the same as getting a head and a tail, or a tail and a head is the same as getting 2 tails, right? Now this experiment is no longer equally likely. And the reason that it's not is because all of those things in there, and how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 things in there, 8 elements in that sample space. They don't all have the same chance of occurring. And because they do not all have the same chance of occurring, we would say that it is not an equally likely outcome experiment. Okay. All right, so this definition down here, though, says if you're working with an equally likely outcome experiment, probability is a simple fraction. Now, I'm using the word simple here. It does not mean easy. Simple just means uncomplicated. Okay? And so suppose a fair die is rolled, find the probability of the following. All right, and I'm going to use this definition right here. And what does that definition say? It says, let S be the sample space of an equally likely outcomes. Let E be the event that is a subset of that sample space. Then the probability that E occurs is the number of elements. Remember that cardinality definition? The number of elements in set E divided by the number of elements in the sample space. Okay. So here are what the problems are going to look like. Suppose that a fair die is rolled. Find the probability of the following. Okay, so my experiment is to roll a fair die. Now it doesn't say what kind of die, so I just know that means a 6-sided die. That means that my sample space is going to be 1, 2, 3, 4, 5, 6. Right? I want to find the probability that the event E happens where E is rolling an even number. So E is going to be the event roll an even number. That's going to be the 2, the 4, and the 6. So then the probability that E occurs. Okay, so I'm using this capital P here. That's my notation for probability. The parentheses tell me that the thing inside the probability is the event I want to have happen. It's going to be the fraction. The number of elements in E divided by the number of elements in S. Number of elements in E, the cardinality of set E is 3. The cardinality of set S is 6. 3, 6 reduces down to 1/2 or 0.5 or 50%. It really doesn't matter how probability is represented. Just make sure that you're representing it the way they ask you to in the problem. If they ask for a simplified fraction, the answer would be 1/2. If they're asking for a decimal, 0.5. If they're asking for a percent, it'd be 50%. Give them the answer they want in the form they want. Okay? Now I know there's at least one person who's watching this video who said, I did not need to do all of this to get that answer. They know that on a die that half the numbers are even, so the probability is 1/2. I am not going to disagree with you. I'm just simply writing everything out so we can see where all the pieces and parts come together to make that formula. Right? All right. Let's take a look at the next one. The number rolled is less than 3. So what is that set F? What is that event F? Gosh, that's ugly. Let's see if I can make that prettier. There we go. Less than 3. Less than 3 are 1 and 2. So then what's the probability of f? Well, there are 2 elements in f. There are still 6 elements in the sample space, so 2/6 or 1/3 when reduced. Now, there are people who will get this wrong because they cannot read this and interpret it correctly. What does less than 3 mean? Well, does less than 3 include the number 3? And that's where they make their mistake. All right. All right, how about the last one down here? Then we'll call this video good. The number rolled is prime. So G is the event. Rolling a prime number. The prime numbers between 1 and 6 are 2, 3, and 5. So then the probability of G is going to be the number of elements in G, which is 3, divided by the number of elements in the sample space, which is 6, reduces down to 1/2. Again, people will get this wrong because they do not know what that word means. The formula for probability is ridiculously simple. Make a fraction. Upstairs goes the number of elements in the thing you want to have in E. Downstairs goes the number of elements in the thing the sample space for the experiment you're running. Okay? Requirements are that it has to be equally likely. Where it gets complicated is the language that is used. If the events are given to you in English written out, converting them to the math can sometimes be tricky. All right, we're at 21 minutes, so I'm going to stop it here. We'll come back and do some more examples. I'll see you all back here for part 2.